So now we're going to use y double prime to find all this stuff, and over here we used y to find all these things here. Okay, so we use the three functions y, y prime, y double prime. So y double prime is the derivative of this thing here. So I'm going to do that in red just to kind of separate it, and then we'll simplify it. Y double prime, using the quotient rule, derivative of the top, negative 2x times the bottom, 1 plus x squared squared. And notice I didn't expand this out because you don't want to expand it out. Then you're going to have this huge polynomial, which you got to derive. It's going to be super nasty. I'm just going to leave it like this. It's going to end up being kind of nice. Not super nice, but a little nice. Like my wife. She's a little nice sometimes. Yeah. Again, terrible jokes. I'm sorry. So the top times the derivative of the bottom, which is, by power rule, 2 times 1 plus x squared to the first times the derivative of the inside, which is 2x. So we got that going on there. And all of that by the quotient rule divided by 1 plus x squared squared. So that's to the fourth power. And luckily now, check this out, we have 1 plus x squared here. Really we have this part, which is derive the top times the bottom, minus this part, which is derive the bottom times the top. And it's all multiplication in there, so we can cancel out this 1 plus x squared. There's 2 here, because it's squared. There's 4 on the bottom, and there's 1 over here. So we can just cancel them out. This is going to become a 1, and this is going to become a 3. So let's come back up here, get rid of this. Whoa. All right, a lot of math going on. The second derivative, simplifying this down now, this is a 1, so I can multiply into 2x. So y double prime is going to be negative 2x minus 2x cubed. Okay, minus, now we got to multiply this stuff out. We have 1 minus x squared times 2 times 2x. So 2 times 2x is really 4x, so we can put these together. Make our job a little easier. Times this stuff. So we're going to get minus 4x plus, because a negative and a negative make plus x squared and 4x, is 4x cubed. Over 1 plus x squared to the third power. There we go. So let's erase this. We're almost done. I know it's a lot, but I'm doing all the work here, really, you big sissy. And we'll put it all together up top. Y double prime is negative 2x cubed plus 4x cubed is 2x cubed. Negative 2x minus 4x is negative 6x. Over, right? Negative 2x, that's right. This is right. Good. Over 1 plus x squared cubed. And we want to know where this is our derivative simplified. We might as well factor it. We're going to have 2x times x squared minus 3, I believe, over 1 plus x squared cubed. Again, don't multiply this out. We want it to be factored. So we want to know where that thing is 0 and undefined, because we're going to create a number line and then divide by, and not divide, I'm sorry, make a number line and test all the intervals for the concavity. Get out of here, dummy. Okay, so this thing is never undefined because the bottom is 1 plus x squared. That's never 0. It equals 0 at 3 places when x is 0 or positive negative square root of 3. And you get that because it's factored. So either this is 0 or x squared minus 3 is 0. And remember, when you take the square root in an equation, you have to take the positive or negative square root. So we have the negative square root of 3, 0, square root of 3. That's what we got going on. And we're going to use our factored form of our derivative to test these things out. Man, how do I keep missing this x? Wow. Okay, so if x is less than negative root 3, like negative 10, okay, just pick it. I always pick negative 10. Negative 10, plug it in. We're going to get 2 times negative 10 is a negative number, times negative 10 squared is 100, minus 3, that's a positive number, divided by the bottom, 1 plus x squared is always positive, so positive. So negative, positive over positive is a negative. That means we started out concave down. Then we're going to plug in a number between negative root 3 and 1. I mean 0, like negative 1. Okay, negative root 3 is like 1 point, I don't know, like 7 something maybe. So negative 1 we'll plug in and we're going to get a negative times negative 1 squared is 1 minus 3, a negative, divided by, the bottom's always positive. So negative, negative, positive makes a positive. And that means here it's concave up. Now we're going to plug in a number between 0 and root 3. Well, positive 1 works. When you plug in positive 1, you get a positive times a negative over a positive. That is negative. That is concave down. Oh, you should put out here, sorry, this is y prime. I apologize a lot too. All right, and the number greater than root 3, like 10, you're going to plug it in and get positive, positive, positive. Here we are. And that's going to be concave up. So our concave up intervals are from negative root 3 to 0, union with root 3 to infinity. And concave down, negative, infinity to negative root 3, union with 0 to root 3. And our points of inflection happen where the concavity changes. Well, that happens at negative root 3 because it goes from concave down to concave up. So our one point of inflection is negative square root of 3. And to find the y value, we need to plug this x value into this. So we're going to get negative root 3 over 1 plus 3. So it's negative root 3 over 4. Okay, that's 1 point of inflection. All right, let's get rid of it. We're done with him. Next point of inflection is at 0, so that's going to be 0, 0. Because when you plug 0 in this, you get 0. And our other one is going to be at root 3. And when you plug root 3 in, you're going to get positive root 3 over 4. Again, you know that because why? Oh, because it's odd. So at the negative x values, you should have negative y values. So we do. So now we got all this junk going on. This was a lot of work, but we're done the calculus here. Okay? Now, what I recommend you do is make a number line, which I'm going to do here. We'll go to the next page. We're going to make a number line. And on this magical number line, we're going to put all of the x-intercepts, the critical numbers, and also the points of inflection. So we need x equals 0, 1 and negative 1, negative root 3, and positive root 3. So negative root 3, negative 1, 0, 1, root 3. And what this does for us, let's make this line a little longer. Get out of here. What this does for us is it splits our graph into sections. And on each section, we can tell what y, y prime, and what y double prime are doing. And that lets us know what the graph looks like, okay? So if x is less than negative root 3, I don't know, like negative 10, that's a good number to pick. Let's go back and check out y. If x is negative 10, we get negative 10 over 1 plus 100. That's a negative number. So our function is negative. Y prime, when x is less than negative 3, is in this interval here, negative infinity to negative 1. It's decreasing. That's really why we want to know what y prime is. We want to know if it's increasing or decreasing. And on that interval, it is decreasing. So our function's negative, decreasing, and the second derivative tells us concavity, and concave down on that interval. Negative infinity to negative 3 is concave down. So our function is going to be negative, decreasing, concave down. If you check on this interval, the function is still negative. It's still going to be decreasing, but now it's going to be concave up. If you check from negative 1 to 0, it's going to be negative. It's going to be increasing, and it's going to be concave. Let's go check this out here. Concave up still. Up. Between 0 and 1, it's going to be positive. After 0, it's still increasing from negative 1 to 1, so it's still increasing. Increasing, and checking concavity between negative 1 and 1. No, I'm sorry, negative 1 and 0, right? No, 0 and 1. I'm sorry. Between 0 and 1, that's up here, that's going to be concave down. So concave down. Between 1 and root 3, it's going to be positive. Let's, again, go back here. 1 and root 3, that's in this interval, that's decreasing. And between 1 and root 3 is 0 and root 3 still, so it's concave down. Concave down still. And after root 3, it's going to be positive, decreasing, because it's decreasing forever after, what, 1, yeah, and concave up. So now we've broken this graph down in all these sections. It looks like a lot, but once we put this on a graph, it's going to be much, much easier. So let's go ahead and do that. You're going to draw your axes, and you're going to put all the points you know on this bad boy. Well, we know it goes to the origin. Let's graph in green. That would be fun. holiday colors. I didn't say Christmas. I don't want to offend anybody. Okay. Green. Here we go. 0, 0. We also know it has to go through the points. What else do we have here? Max is at 1 at 1/2. Min is at -1, -1/2. So it has to go through -1, 1, and it's going to be 1/2 at those points. -1. So I forgot already. What is it? 1, 1/2, -1, -1/2. So 1, 1/2 is going to be like right here. -1, -1/2 is going to be like right here. We could put the coordinates there. 1, 1/2. -1, -1/2. Okay. We know 2 more points. They're points of inflection. -√3, -√3 over 4. Well, -√3 is between -1 and -2 somewhere. And -√3 over 4 is a little bit bigger or less than -1/2. So it's going to be like down here somewhere. And I'll put the coordinates there. That's -√3, -√3 over 4. And that's probably going to be in the way of my graph, so I should move it. I'll move it over to here. All right. That's a 3. Cool. And then we're also going to have, so that's 1. This is going to be 2. We're going to have the point +√3, +√3 over 4. Okay, that's that point there. And we also know the end behavior is a horizontal asymptote at 0. So on this end, it's negative. So it's going to be horizontal asymptote back this way. On this end, it's positive. It's going to be horizontal asymptote on this way. And now we have these intervals from -infinity up to, no, -√3. This point's really, it's not a 2, I'm sorry. It's like right here somewhere. Same thing with, there you go, that one's good. It's negative decreasing concave down. That looks like this. Right there. From -√3 to -1, it's negative decreasing concave up. That looks like this. Okay? And we know the slope is 0 at -1 because we found that as a critical number. So you should put that on there. We also know the 0 is, it's 0 at 1, so it's going to look like this. There's a maximum. From -1 to 0, it's negative increasing concave up. That looks like this. From 0 to 1, it's positive increasing concave down. That looks like that guy. From 1 to √3, it's positive decreasing concave down. That looks like this guy, even though it's not the neatest thing in the world. That's okay. And from √3 to infinity, positive decreasing concave up. Looks like that guy. And that's what your graph looks like. If you graph them on a calculator on this window, it looks just like this. All right. That was a lot. Good job.